Okay, welcome everybody. Today the conference is going to be English. We come with the person of Manfred Kraus. I'm going to give you a brief review. He got his PhD in 2016 at RWTH, Aachen, Germany. After that, he was a postdoc at Humboldt University of Berlin, Germany, from 2016 to 2019. Then he got a postdoc at Florida State University in USA until 2023. And nowadays he's an investigator associate at Bnfac. So he's going to give us the talk, spinning black holes and gravitational radiation. So please go ahead, Manfred.
Thank you. First of all, thank you for the invitation, and hopefully the next time I can give the talk, it will be in Spanish. So yeah, I will be talking about rotating black holes and gravitational radiation. Just from the title, it sounds like that this is something you would compute in classical general relativity. But I would like to, in this talk, I will explain to you in two examples of how you can actually use modern scattering amplitude techniques in quantum field theory to actually compute things for gravitational waves that have direct impact on, for example, LIGO analysis. So please stop me every time you get stuck or something, or I'm too fast. So we start with a quick motivation. General relativity is by now over 100 years old, and Albert Einstein came up with the Einstein equation, where on the right-hand side you have like the curvature of space-time, which is essentially parameterized by space-time dependent metric, and on the right-hand side you have the energy matter content of the universe. So in the end, it's the curvature of space-time will tell how matter is supposed to move within its curved space-time, and the position of matter in the universe will actually tell how stasis has to occur. It's a highly coupled system. From general relativity, we got very important predictions, mainly one that the universe can be an expanding universe. Albert Einstein also figured out that there will be black holes, that there will be like partial similarities. But most importantly, he predicted the existence of gravitational waves. And gravitational waves have very nice properties. For one, they propagate at the speed of light. And this already tells you, like, if you think of gravitational waves, like electromagnetic waves, that they are mediated by some kind of particle, like the photon, that corresponding particle has to be massless. Otherwise, it will never be able to travel at the speed of light. Like the photon, the hypothetical particle that will play the role for gravity will be the graviton. The graviton also has two polarizations, and this is one is the so-called plus polarization, where you see that if you have like test masses and the gravitational wave will hit these four test masses, they will be either stretched and compressed either in a form that looks like a plus, or on the right-hand side like a cross. So it's this stretching and squeezing of space-time that actually produces then signals for the gravitational waves that we can measure. So the main problem is we now want to study gravitational waves. So we have to somehow induce a time-dependent oscillating curvature of space-time, and we have to put in some kind of matter to generate that. It turns out that this proportionality factor here is something like 10 to the minus 30. We actually have to put in a lot of mass to make it dent in space-time. So we are not talking here about like the moon goes around the Earth. So you really need really massive objects like black holes. And that's what we would like to study. Going on, the first indirect observation of gravitational waves was in 1982, and this is is an indirect observation where so shortly before, 1974, Taylor and Woods discovered the first binary neutron star system. So you have two systems that spiral around each other, and over time they will come closer and closer and will become faster and faster until they collapse. So if the system emits gravitational waves, then the two neutron stars will come closer to each other faster, because you're radiating away energy from the system. So in order to preserve angular momentum, the radius becomes smaller and they have to get faster. So now they observed this binary star system over a period of nearly 20 years. Nowadays it's even longer. And you see in red here the measurements of how much closer the system comes. And then in black you have the prediction of general relativity that already includes the effect of gravitational radiation. So this is the first indirect observation that gravitational waves actually exist. So we had to wait another 30 years to get direct observations from LIGO in 2015. And they found a gravitational wave. So LIGO are essentially an interferometer. So you have like two arms that are 4 kilometers long, and you just measure the length of each arm with a laser to a precision of below the radius of the probe. So now if the gravitational wave hits the system, then one arm will be slightly longer than the other one. So your interference pattern in your interferometer will change. And what you observe then is this zigzaggy waveform. So this is the gravitational wave that they have measured. There's a lot of things in there, but in simplified view, this is what they measure. And the theory prediction was, they tried to obtain this waveform from numerical relativity, and they found something that looks very similar. Because you now have a simulation that tells you, okay, this waveform corresponds to these masses and these angular momenta. You now know that this signal, what they discovered, it actually belongs to two black holes falling into each other. So what I will be talking in the following about is what we can do on black hole spirals or neutron star spirals. But it's like compact binary systems that we want to study in general relativity, but coming from a quantum field theory perspective. So then afterwards, LIGO started collecting more and more events. I think by now we have like 100 or 200 binary collisions measured. But what you see is that while each of the gravitational waves looks a little bit different, they all have the same kind of key features. There's a very long in-spiral phase here where the two black holes are very far away from each other. So they just start going around each other. So this is very periodic motion. And while they are emitting gravitational waves, they become closer and closer and faster, which you see that the period, the frequency will start to increase. So once the black holes get close to each other, they will actually start to merge, and this is a very violent oscillation pattern in the middle. And then finally at the end, you have like the ring down. You have the new black hole is formed, and it's still emitting gravitational waves because it has to find a new static solution. So it's like you have essentially like an excited black hole which has to radiate away energies to go to the ground state. So while all of these three stages are shared for all of these events, and they might look different, or for example, with neutron stars, they can go periodically going on for a long time before they merge. But all of the ingredients are there, and this is what we are especially interested in. So the gravitational waveform in a typical analysis, you can extract this waveform here directly from numerical solving the Einstein's equation. However, the problem will be that a typical LIGO analysis, like the ones that are with the very first observation, you need about 250,000 simulations in order to do the statistical analysis. However, computing a single simulation for black hole merger takes about 10 to the 5 CPU hours per simulation. On top, you will have problems in challenging cases, configurations, like one black hole is very much heavier than the other one, or you have a system that is very fast, the immediate speed of light, or if in case of spinning black holes, if they have the maximum allowed theoretical angular momentum. In these cases, these numerical simulations become really difficult. So in order to make such a analysis feasible, the solution is actually to use something like semi-analytic models. And the main part is that we can actually do perturbation theory here in the beginning and here in the end. When the merger is happening in the middle, you have to rely on numerical relativity to get the correct answer. And these semi-analytical methods, they usually rely on some kind of expansion, and historically tested was the post-Newtonian expansion, and all of these things are combined via an effective one-body approach. I will talk a little bit about this in the end. What happens essentially is if you work on these post-Newtonian expansions, you get higher order corrections to the Newtonian potential, and you can essentially solve these equations of motions and simplify. Okay, so first thing, what is our analytic toolbox? If we want to do something analytically, not numerically, then we have to know what to expand our theory. So there's, as already mentioned, traditionally post-Newtonian expansion. This is what people in classical general relativity would use. This allows you to describe a binary system that have a large separation and are slowly moving. And this is essentially like a double expansion in the kinetic energy and the potential, because those are linked by the Villiers theory. So you can actually compute in here bound orbits in this expansion. So what we in quantum field theory prefer more is the so-called post-Minkowski expansion. So we have still large separation, but we have relativistic black holes. The problem is that this is very useful in describing open systems like scattering, like how you would do this in particle physics. You never think of in particle, you rarely think of it in particle physics that okay, you have like a bound system. Like mostly at the Large Hadron Collider, you are interested in you're colliding two protons and some bunch of particles are coming out. So now we are colliding black holes and two other black holes come out. And this expansion essentially just assumes that the Newton constant G is small. So this is very typical also in quantum field theory. You have a small coupling constant. You're not doing in simultaneously a small coupling and a small velocity expansion in quantum field theory. And at last, there's something that is called gravitational self force. This is just here for completeness. Here you can essentially order, you can work to all orders in Newton coupling, but you expand the theory in mass ratios, where one black hole is very much heavier than the other. So all of these are complementary, but what we will focus on in the following is the post-Minkowski expansion. So now you might think, okay, but I want to describe black hole gravitational waves from e-spirals. If I now use a method that only can describe open orbits, scattering of black holes, how does this come together? Like, why do we even care about this? Yeah, so for bound system, you would get your oscillation. For an open system, for scattering of black holes, you would just get like a click, and that's it. So the question is, why do we do this at all? This doesn't seem to have anything to do with it. So the one point is, okay, this we can describe in quantum field theory, And the effective one-body approach can make use of these results. Because if you think of it in classical general relativity, the difference between scattering and bound states is simply a matter of initial conditions to your Einstein. The physics is the same that is happening, but it's a matter of initial conditions. So how does this putting it back together work? So in order to these analytical models, we're using the so-called effective one-body approach. And it's very similar to what you would do in a hydrogen model. You have like two objects that move around, like in the hydrogen, the proton and the electron going around. And the main difference is in the proton is way heavier than the electron. Here, you will have proper, they are kind of the same, they can be anything. But it's the same thing, you just go into the center of mass system. So you have like an effective black hole solution in the middle, like an effective black hole with some effective angular momentum. And now you describe the gravitational wave by solving a test particle motion in that effective space-time. So you can describe then this situation here using a Hamiltonian approach. And this effective Hamiltonian essentially describes space-time curvature, but with unknown coefficients. So for Schwarzschild, you might know that this becomes like a Schwarzschild wave. But for us in this model here, these are three parameters. We can parameterize them by unknown coefficients. So these unknown coefficients are now matched to the full calculation. But since the difference between open and closed orbits is just initial conditions, we can use this effective one-body approach to look at scattering events, extract A and B, and then use it with different initial conditions to actually obtain the bound orbit. So in that way, our approach can actually contribute to the simulation of the gravitational wave. So in the end, everything that we're computing goes into extracting this effective space-time approach. Other questions so far? Okay. So does it work? For example, if you take, so in blue we see a gravitational waveform that is obtained from numerical relativity. So this is the truth. This is what we want to obtain in our analytic model. If we don't do anything, we already get something that looks similar, but it's off. So now if we calibrate, that means we are extracting A and B from our computations. Then we already get very close to the spiral, but then later on the signal can become a bit different. So then the last thing is we can include what's called non-quasi-circular corrections, because most of it is you have a parameterization for circular. Spiral might be elliptic, so it doesn't need to be circular. So if you include these corrections as well, then you are essentially spot on. And the effective one-body approach might take like 1 second to generate this waveform, while you have to spend a month on a supercomputer to get the numerical relativity result. Okay, then how do we make the connection to scattering amplitudes now? First of all, one should keep in mind that in quantum field theory, scattering amplitudes are very nice objects. They have a lot of mathematical structure, but amplitudes themselves are not physics. Amplitudes themselves are not observable. And for example, if you look at an L-loop Feynman diagram or amplitude, they will typically scale like as 1 over h bar to the L plus 1. That means you have a lot of quantum or even what we call super classical forms. Typically, these loop amplitudes also have divergences. So, but all of these things somewhere in these scattering amplitudes, there must be the classical information. So the question now is how can we extract it from? So the key point here is we have to relate amplitudes to actually observables, because observables must be well defined, must be finite, and must have a classical limit. When we can do this in various approaches, one is, for example, to extract directly a classical Hamiltonian out of these scattering amplitudes. So, for example, if we would do this, then we can essentially match directly with the Hamiltonian of the expected one-body approach. The other way is to compute observables by direct integrated computation. For example, you want to know how much in the scattering the momenta, the impulse of the black hole is changing. And you can relate this to some tree-level calculations plus some root calculations. So it's very similar to what you would do in perturbation theory in particle physics. There are some other approaches which I don't want to go into detail about here. So in the following, I will give you like one example where we expected this Hamiltonian for spinning black holes, and then another example, a very quick example of a direct computation of from first principles to compute directly the gravitational wave from amplitudes. So how do we get out of quantum scattering amplitudes in classical physics? So long-range interactions, they actually sit in a phase space where you have a lot of very soft gravitonic changes. Think of it, if this here is an electron, this other is an electron, these are photons, you essentially would get back Coulomb potential. You can get really like the classical electrodynamics back from these kind of techniques. So the idea here is you have a lot of graviton exchanges, and all of these exchanges, these momenta that you exchange, are of the order of h bar. And they are way smaller than the masses of the black holes involved or the center of mass of these things. So now you essentially have to expand your amplitudes in h bar. So it first sounds kind of crazy that you use a quantum field theory that intrinsically has quantum corrections. And now you try to get rid of all of the quantum stuff in order to get the classical piece back. But it turns out that this is more efficient than solving analytically Einstein's equations. So what we do, we use what's called expansion by regions, which tells us how to expand systematically in small h bar. And in loop amplitudes, we essentially only to take into account that the loop momenta are of the order of the exchange momenta, which are of the order of h bar. And this essentially leads to something that has called the potential region. This is like conservative physics. So this means you can write those terms. If you compute in this region, you can compute the Hamiltonian. You can extract more like radiation effects. If you're really interested in the radiated away energy of the system, you only have to compute a little bit more. At higher orders, these things are not very well distinguished, but they are very good at the beginning to get a hang of what to do. Okay, let's start by looking at the classical Hamiltonian of a black hole. And what we essentially want to do, we want to map the system where you have one spinning black hole and one Schwarzschild black hole that are very far separated onto loop diagrams in a quantum field theory. So what we essentially do is we're using Einstein-Hilbert, like we just take the Lagrangian of general relativity and treat it as a low energy effective quantum field theory. You have to couple point particles to gravity in order to simulate either non-spinning black holes, spinning black holes, and you can include other fun stuff like finite size effects if you're interested in neutron stars, or if you want to study higher spinning things, you will have to include higher spinning quantities. So how does this work in practice? So let's say we have like this is like a heavy scalar, this is another heavy scalar, and they're exchanging gravitons. So now you can compute the Feynman diagram that corresponds to this, and you get something that looks like this, and you see, okay, here's 1 over q squared plus something that is less than 1 over q squared. So q was of the order of h bar, so this thing goes like 1 over h bar. So this is like the leading piece. If you now start to Fourier transform this piece, you already see that something like the Newton potential comes out. There's some weird factor here. But you notice if you go now to the non-relativistic limit, where these black holes are not moving, you really get Newton. So what that means is that from scattering amplitudes, you can actually perturbatively compute the potentials, corrections to the Newtonian potential. And these scattering amplitudes will give you the fully special relativistic corrections to these potentials. So now if you want to compute higher order corrections like t squared, you would have to change exactly gravity. So you have to deal with the one loop computation. You want even like g to the 3, you have to change 2 more. So then you have to deal with 2 loop scattering amplitudes. So the theory that we're using is really like the Einstein-Hilbert, which you might have seen in general relativity. And then we're just coupling to gravity in a minimal way, either scalar particles or massive vector bosons here. And now you have to expand your spacetime metric G around flat spacetime, and the fluctuations in your spacetime are then the so-called graviton cubes. So this is the photon in QED. You will take here the fluctuations in the metric spacetime will be the graviton field that we will experience. So the problem is that general relativity is nonlinear. So if you have a G with upper indices, it has an infinite expansion in kappa. The same you have with this the determinant of the metric here. It has an infinite expansion. That essentially tells you that your Lagrangian has infinite many terms. And you have infinite many Feynman rules to take care. So you get like you have 3 graviton interactions, you have 5 gravitons, n graviton interactions, you have 2 scalars with 1 graviton, 2 scalars with 2 scalars, and so on. So it's only like the specific amplitude, only a certain subset of these things actually contribute, so you don't really have to deal with all of them. They're infinite many. So what do we compute in the first place? We now compute the scattering of the massive vector boson in scalar, also the massive scalar, in gravity. So now, for example, at one loop, we only have to compute the box diagrams and these triangle diagrams, where here in black is the ground plane. And that's all. That's where all the classical physics is hidden. At two loops, you have to compute this subset here of the full amplitude, and all of the classical physics is hidden in these kind of diagrams. So now you are essentially faced with 2 tasks to do. On the one hand side, you have to extract classical information from quantum amplitude. And on the other hand, you have to relate the quantum spin. You have to spin one particle that has spin down, spin up, and spin longitudinal to the angular momentum of a rotating black hole. So this thing will be a bit tricky with this thing. But in the end, this is rather straightforward. It's just very unusual because in particle physics, you never really think about either of these 2 tasks. Okay. first thing that we have to do, what we're trying is, so I assume everyone here has seen like time and light something like this. You know that for the vector boson, we have like polarization vectors. That's essentially where all the spin information of the massive vector boson sits. And now we would like to decompose our matrix element into some scalar coefficients and something that encapsulates the complete spin dependence. So the only thing that you can write down are these four things here. Okay, we are not going into details here, but you have four, like the fifth one here with the plus sign vanishes after doing all of this stuff. So you have four spin-dependent tensors that you have to take care of. You can compute now numerically what are these scalar coefficients. Not so important how we do it, but it's just you have this decomposition of scalars and the spin part is separate. So how do we do this computation in the first place? How do we compute now all of these diagrams? Because just writing down the loop Feynman diagrams for these things would be horrible. So you're really like, if you try to do this in a textbook approach, then each of these diagrams will be 1 gigabyte just of expressions. So there's no way you can do this by hand, but there's also no way you can really put this on a computer in a systematic way. So you have to be a bit clever of how to actually compute those group contributions. Next question so far, because the next two slides are like difficult. So how would you typically do this? You just write down the sum of Feynman diagrams. So you have like some loop propagators, you have some numerators, and then you have to integrate all of your loop omega. So now you typically in the first step, what you're doing is you're applying integration by calculations. Or to do one loop calculations, you would do like Pasadena-Feldman reduction. So you want to end up with master integrals and some coefficients. These coefficients only depend on kinematics. And then you have to integrate so you get only coefficients and process-independent master integrals. So this is what you would typically do, but the main problem is here part one. In gravity, first is what is always the problem, just writing down the limits. Yeah, like if you try to, I think 5 loops for graviton scattering. The number of terms on the Feynman diagrams is more than particles in the universe. So it's just impossible, you can't do it in the Feynman diagrammatic approach. So we are now taking an idea which is called generalized unitarity, and we are essentially stripping off the amplitude, the integration. We're just looking at the integrand as a function of loop momentum. So now your integrand is a sum of numerators with certain propagator powers. And your numerator, you just make an ansatz. You just write down the most general polynomial in the loop momenta, like L squared, L dot P, L dot P2, stuff like this, with unknown coefficients. So now we want to extract these coefficients. And we're using the fact that we have a very powerful factorization theory. Namely, if you take this integrand, you multiply with the propagators, like one of the full denominators, and you send all of these denominators to 0. Then the corresponding numerator that is evaluated on the loop momentum in which all of these propagators go to 0 will factorize into a product of 3-level variables. So if you have, for example, 4 gluon bots, you send all of the propagators to 0, then you have a product of 4 3-point amplitudes. So, but now I've reduced the problem of writing down a Feynman diagram for a loop topology to computing three-level amplitude and just multiplying them together. So now you can take this ansatz, if you just compute product of three-level amplitude on sufficient numerical points, and you know your polynomial basis, which you also evaluate on the same points. So now you have a system of linear equations to extract your coefficient function. And this is very optimal to do it, like it's very efficient. And this is the way how we compute all our diagrams. And just to give you like an idea of how this works. So you have to organize your calculation in a hierarchical way. For example, you have like here these double boxes. But now you could, for example, remove this propagator and then you land here. Now you can remove this propagator and you land here. Yeah, there's a structure behind why we order them like this. So let's focus here on this double box. What you do is, okay, I evaluate the three-level amplitudes. If I cut all of these things here, then I have 1, 2, 3, 4, 5, 6 3-point amplitudes that I have to multiply together. And I have my ansatz for the numerator. So I just do this sufficiently often, and I can extract my coefficients, and I know what is the double box in between. So if I now go to the bottom one, I can do the same. I can compute the corresponding three amplitudes to this integrand. I have my parameterization. But now the problem is that most of the propagators here are also propagators here, except for this one. So now I actually have to subtract contributions from the thing that I already know. But in the end, if I do this, I also get contributions from here because I can use this like here. So in the end, I would be also able to write down a system of linear equations for this topology and also get my difference. And then in this way, just by iteratively computing three-level amplitudes and fitting the integrand, we can compute the whole two-loop amplitudes. So essentially what we are using is the fact that we can decompose multi-loop amplitudes into products of trees. All of these, we are now essentially computing loop amplitudes simply by using linear algebra. It's nothing complicated anymore. And the integrands of the multi-loop things are computed from powerful numerical recursion calculations. And all of this we have like implemented in a program that is called Parallel that allows us to do these things as efficiently as possible. Because we're talking here still about this is one of the most efficient ways to do, but it's still like computing the thing, it's still like a day on a computer. So what I have achieved so far, we have written our amplitude in terms of coefficients functions, we have master integrals, and we have our string tensors. However, all of these things, the coefficients, the integrals, and the tensors depend on h bar. And the tensors in the end are also functional with the string. So now we somehow have to dig this out. So we have to kind of send now h bar to 0 and expand our quantum amplitude. How do we do this? You just impose classical scaling that we did at the beginning, namely that L is proportional to h bar, and then you use like this P, Q also goes like h bar, but P bar doesn't. And what we use then to see is, for example, the box integral. We have an h bar to the 4 from the measure, we have 1 over h bar to the 4 from the master's graviton propagator. But then these massive propagators, they will turn into linear integrals, linear propagators, which make the thing simpler. But overall, the whole integral starts with 1 over h bar 3. So you want to go up to the classical piece that is h bar to 0. This is what you have to keep track of. In the multi-loop amplitude, it's very nice. For example, if you have high tensor inputs in your amplitude, they're immediately of higher orders in H bar. So a lot of those you don't even have to keep track of. You just throw them away from the. And in this way, you can systematically expand all of your intervals. The next thing is, how do you extract classical spin information from a quantum space? And here the idea is that you use, first of all, it has to be a massive momentum. Because what you're doing is you're writing the polarization vector for spin S as the Lorentz transformation of the rest frame polarization vector. So you have then, you can write down this Lorentz rules that brings it from the rest frame to some arbitrary moment of T. So now all of the H bar dependence sits in this Lorentz. And now you simply expand this thing. So then in the rest frame, you have spin one particle, so it's like normal relativistic quantum mechanics. You have the basis of your polarization states. And now you can relate expectation values of like contractions of these things to spinning expectations. So for example, if you have like the identity, then simply this is just a scalar product between the two states, which then becomes a scalar product between the two rest frame polarization vectors. You also have the spin one representation, like in SU2, in quantum mechanics for spin one half, you have the Pauli matrices. For spin one, you get this epsilon tensor. So in that sense, we can relate all of these tensors of polarization vectors to some kind of spin multiple in our computation. And now if you start to expand those four tensors that we had at the beginning, you now see that these become linear combinations of other stuff. And now you see here you really have all of your spin multiples in the amplitude. And for example, here O2, Q cross P will become L once the Fourier transform into position space. So this is something like L dot S. So this is like spin orbit coupling, which you might know from the Zeeman effect. So this is kind of like a similar effect on duality. And of course you get a whole tower of higher order multipoles. So now we've seen, okay, we can expand things systematically to the H bar, we can relate to spin. So now these amplitudes have an expansion in Q. And typically the second loops are involved, we get like a power law expansion. And the classical limit always sits one guy deeper. So the question is now, how do we do this systematically to get out the classical pieces? Because the one loop has something that scales like 1 over H bar. So if you send H bar to 0, the thing is not even quantum correct, it's not classical. It's something that is even stronger. And it turns out that these things are well understood. I don't want to call them unphysical, but we don't dare the iteration of lower things that you already know. So the question is, how do you extract all of this now systematically? And this, typically, if you want to get the Hamiltonian, what you do is you do a similar calculation, but in an effective field theory, where you only take the degrees of freedom that you actually want. So we have like a non-relativistic, non-local, classical, three-dimensional effective field. So what do we try to achieve? We essentially try to integrate our gravitons. And that is clear that this will not work in a proper way. Like you cannot integrate out the photon out of Q. You get something that stays local. So there will be a lot of momentum dependence, for example, in these directions. You also see that we typically have like quadratic in the derivatives for kinetic terms of the particles. But here, since this is a classical theory, you don't want antiparticles. So you just take these kind of kinetic terms. but you also, this tells you already like the propagator will be linear and will have a very awkward form. So then the potential is essentially parameterized by some coefficients that are momentum dependent. And this is where this non-locality comes in. These are the things that we actually want to extract. In order to span the spin space, we have to take our spin multiples. And then we just do the same calculation and we just try to equate those calculations and obtain what are these matching coefficients. In the end, you just have to compute this iterated bubble integrals, and this will give you the full Hamiltonian. So, for example, the first part is the thinness part, which just corresponds to the identity operator, and you now have like an series expansion in powers of g, and we already saw that we get this here as a Newton potential, then you get the one-loop corrections and the two-loop corrections. So this has been computed before. This we reproduced, but in our case, obtaining this is a very non-trivial step. It's not just following the step that they did. And as a second, it's more messy. The spin-orbit coupling is one of the most important terms in the Hamiltonian. You get very messy results, but the thing is also a new result and is at the moment employed in these simulations for gravitational waves. The other operators that O3 mods for are much more complicated, and I can't fit them on screen. But when we checked our calculation, that we used this Hamiltonian, and we actually computed some specific observables, and we found complete agreement with a different approach that uses something, a completely different method, which is called the word line quantum field. So this is all that I want to tell to the Hamiltonian. And now very briefly, I want to talk about gravitational radiation. So this is like, we try to compute not a Hamiltonian, but we want to directly compute the gravitational waveform. So the connection between what is the waveform and what is in terms of amplitude is rather elaborate program. So I recommend reading this paper. It's not very easy to digest, but in the end, this is what we need to do. In the end, this is also, you have some classical amplitude that you have to Fourier transform to get the waveform out. In terms of amplitudes, at leading order, this is like a 5-point amplitude. Like, think of this is like one scalar, this is the mass effector boson, now you're radiating explicit graviton now. At one loop, you get contributions from one loops and essentially like 3-level squared contributions. But you see that this is like 5-point interfered with 4-point. So this is a little bit different than what you would usually see in particle physics. So I don't want to spend much time here, but what you see is most of this work has been done in 2003 and 2004. There has been a lot of work on the spinless case, especially since the very first calculations, they missed some effect, and there was a lot of controversy that had to be resolved in order to figure out what is the correct result. Including spin, most of these things were done at leading orders, but for all orders in spin. And last year in Christmas, we were actually able to compute the very first linear spin effects next to the leading order. And it's very similar with the classical limit. You only have to now, before we had one Q, now we have Q1 and Q2, but both of them are scaling like H bar. So things, the classical limit is again just an H bar expansion, but kinematic generally is a bit more complicated because you have 5 particles. But in the end, you have to compute these kind of one loop 5-point diagrams. And the necessary loops in general are these here. Classical physics is all hidden in here. Even though like we see that the expansion in the H bar simplifies a lot the scattering amplitudes, the resulting expressions that come out in the Python pages are still very, very complicated. You really have to be smart to handle those, because it is very quickly that you get like a 200 megabyte result, and then what do you do with it? The spin decomposition of these things is also a bit more complicated. You have something like an identity. Now you have epsilon tensors with spin momenta and spin. You have spin squared operators and so on. So in the end, you find up to 20 independent spin multipoles in this amplitude. And so far, we've only focused on the linear terms because they were already horrendous to compute. We're currently looking into the spin squared things, but I think we have to be a bit smarter. So you just compute these diagrams, you take h bar to 0, and you decompose as before the polarization vectors in terms of spin, and then you can Fourier transform this matrix element. So now the spin independent part, you will see here you have a plus, and the cross polarization is mentioned in the beginning, and they look very different. And also you don't see the oscillatory pattern because this is scattering of black holes. This is not the bound thing. But you see that the corrections between leading order next to leading order are actually huge. Like just looking at the magnitude of order, this is like 0.1. So these loop corrections are actually very important to get the physics correct. So I cannot show you the spin-dependent waveform. And the reason is we were not able to obtain a numerically stable Fourier transformation of these expressions. There's still more work to be done on this side. But on even like in higher spin things, these things become more and more complicated. I think what has been done at the moment in the literature cannot be pushed to higher multipoles. It's enough to conclude. So what we have seen is that classical gravity is like a playground of a lot of different field theoretical approaches. And from scattering amplitudes, using all kinds of methods, like we use generalized unitarity. There are BCFW, double copies. There are also KLT relations that are inspired from string theory and everything. All of this can be applied to obtain results in classical gravity. We have to deal with finding into integration, but we know a lot of technology of this due to the Large Hadron Collider program. So we can import everything that we know from particle physics to classical gravity. In the end, we also have effective field theory methods that in order to extract certain things in a systematic way. So essentially, everything that you learn in particle physics will have a place here in terms of classical gravity. The outlook is that there's still a lot of things to be done. For example, one can look at the scattering of two different spinning particles. Then you can obtain Hamiltonian of spin-spin interactions. Or you can go for higher spin things like a massive spin 2 particle in order to get even higher spin multipoles out of the computation. You can study finite size effects that will be important to study neutron star physics. And of course, you can compute directly higher spin gravitation waves. And so there's a lot of things to be done. That's all that I wanted to say. Thank you.
Thank you. Thank you for this very nice and a lot of work around this topic. So please, someone that has questions, go ahead.
The spin-dependent form you said you can include is the one in which they are rotating, in which the black holes are rotating.
Like here?
Yes, and the one that you say you can find a stable solution.
So we have obtained this result from a computation with spin, but in the spinning part, you will also find the non-spinning part. So this would be the waveform from from structured black holes colliding. So we have essentially, we have computed here the classical amplitude for the spinning part, but then the rest of this integration becomes unstable. We have some results, but we're not trusting them in order to put them into the paper.
Okay.
So we want to do more cross-checks here.
Okay, but you said those are the black holes that are scattering.
Yes.
But they are not.
They are not colliding, but as mentioned at the beginning, let's see, introduction. Because the difference between orbiting and scattering is just initial conditions.
Yes.
You can fit this onto the effective space.
Okay.
So you can still make use of it. It's not academic. Other questions?
Another question. Now, what do you mean by superclassical contributions?
Superclassical are these that are going like 1 over h bar, which would tell you, okay, the classical limit doesn't really exist because there's something divergent.
Okay.
But what happens is, so this superclassical term, this C1 is essentially C0 squared. And here C2 superclassical is this thing cubed. This thing will be more complicated, it will be linear combination of stuff. But it's just information that you already know. And these things will drop out if you do this matching effectively.
Kevin is here? No? It's on the. So he has a question that is related with the source that could generate the gravitational waves.
Okay.
What would be these sources? Remote sources.
I mean, it's the two black holes moving around.
Yes,
that's the source.
And Carlos? He asks, how do you obtain amplitudes for higher spin gravitational waveforms?
So what you would have to do, so the important part is that we are not modifying gravity. Like it's not a higher spin gravity theory. We are keeping gravitons as they are, but we are using a different massive test particle. So for example, here we have used spin 1. We could have used this fermion, massive fermion, because it also has spin. The easiest thing here to do is massive spin 2. Like it's not easy in practice, but it's conceptually the most easiest thing to go further. So a massive spin 2 has a Lagrangian that goes over like 3 lines here. Of course, Feynman rules will be a mess. Amplitudes will be a mess, but you will be able to extract higher spin multiple amplitudes. And all of these things are at the moment unknown. Like there's nothing known beyond quadratic spin at the moment.
So someone online, do you have questions? Please open your microphone. Well, if no, we thank you again. Someone from the Kevin mentioned that you could share your presentation in
Yeah.
order to.
Yeah, Jonathan.
Okay. So thanks again, Dr.